Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
This is a slickline operation. Over the course of a morning, the crew will make 6 trips in and out of the well to replace 3 gas lift valves with 3 dummy valves. This procedure is required in order to prepare gas lift wells, such as this one, for stimulation with acid. Acid has been used to stimulate oil and gas wells since 1895. Today, acidizing is one of the most common well stimulation techniques. Acid treatments are currently classified as 3 basic types: the acid wash, matrix acidizing, and acid fracture. Acid fracturing requires relatively large volumes of acid. Such treatments are common practice on low permeability wells. Acid wash and matrix acidizing use small volumes of acid. These treatments remove wellbore and reservoir damage. Such damage is common in initial completions as a result of drilling, cementing, and perforating, and in older wells as a result of workover fluids, scale precipitation, and fines migration and swelling. All acid treatments require proper justification. This should be based on evaluation techniques such as pressure transient testing or anomalous well performance. Such studies can also preclude the inappropriate and even harmful use of acid on wells that show reduced production due to pressure depletion, changing fluid saturations, or changing surface or downhole operating conditions.
Welcome to this module presenting the fundamental concepts and engineering practices of acidizing. Upon completing this module, you should be able to define the objectives and parameters of acid stimulation, recommend and design an acid treatment, and safely and cost-effectively implement one. In Unit 1, we'll introduce the various types of acid treatments. We'll show how to calculate anticipated production increases resulting from acid treatments and describe the chemistry of the most commonly used acids. We'll include a list of the additives that may be necessary to optimize the effects of acidizing treatments. In Unit 2, we'll discuss the design methods of acid treatments. We'll illustrate the decision-making process with 2 case histories. And then we'll return to this job site to observe the procedures involved in the design and execution of this matrix acid treatment. We'll review the on-site equipment and discuss safety and quality control measures that should be considered on any location.
Let's begin by defining the 3 basic types of treatment: acid wash, matrix acidizing, and acid fracture stimulation. An acid wash treatment removes debris from within the wellbore and the perforations. Acid does not penetrate the formation. The procedure consists of putting acid in the wellbore and allowing it to dissolve the soluble material. Acid may need to be agitated or circulated back and forth over the perforated interval. Also, since it is difficult to accurately spot or place a small volume of acid, 250 gallons is generally considered the minimum. Matrix acidizing removes more extensive near wellbore damage. Acid is injected into the formation at pressures below the pressure at which the formation would fracture. Acid injection rates vary depending on reservoir permeability and the extent of the damage. Once the damage is removed, injection rates can range from 0.25 to 1.5 barrels per minute in reservoirs with permeability less than 500 millidarcies to 1.5 to 3 barrels per minute in highly permeable reservoirs. Treating below the fracture pressure is especially important. If the formation is fractured during the treatment, acid will be diverted into the fracture and bypass the damage. Once the well is in production, the fracture could quickly become blocked with the damage, and the acid treatment will have been a failure. Additionally, fracturing during a matrix acid treatment can establish harmful communication with adjoining water or gas zones. Matrix acidizing has virtually no benefit for an undamaged well. Flow channels, or the effective well bore, may be enlarged by the treatment, but only slightly, since acid penetration into the formation is very shallow, usually only a few inches in sandstones and up to 12 inches in carbonates. Since an increase in production from treating undamaged wells is solely related to any increase in wellbore radius, the negligible effect can easily be shown. To make the point, let's take the extreme case where a matrix acid treatment dissolved the formation to a distance of 6 inches from the wellbore. One way to estimate the post-treatment production increase uses Darcy's radial flow equation. Comparison of natural and acidized production rates is reduced to a simple ratio where the natural log of the drainage radius divided by the wellbore radius is divided by the natural log of the drainage radius divided by the acid-altered wellbore radius. As shown in this example, only a slight productivity increase of 1.11 times the natural productivity could be realized. On the other hand, significant production increases can be realized from a matrix acid treatment when skin damage is present. The same method applies, only the skin factor term is added. For example, if a well had a calculated skin factor of 10, we could anticipate a production increase of 2.4 times the pre-acidizing rate. These calculations are only applicable when a matrix acid treatment is used. In situations where the formation is fractured and the induced fracture remains open, then other methods, such as the Maguire and Sakura curves presented in PE 305 fracturing, are appropriate and indicate that production increases up to 10-fold could be realized.
Remember that in a matrix acid treatment, the injection pressure must remain below the formation fracture pressure. The injection rate, therefore, is very low, and the acid will effectively become spent before it can be pumped into the formation more than several inches.
Fracture stimulation using acid has been successfully employed on low permeability carbonate reservoirs and occasionally on sandstone reservoirs with extensive deep damage. This type of treatment results in acid penetrating hundreds of feet into the reservoir through a hydraulically created fracture. The fracture maintains excellent conductivity as a result of the acid etching flow channels deep into the formation and/or removing sufficient non-recurring damage to allow fluid to flow. The uneven etching pattern on the fracture walls prevents the fracture from healing after the treatment. Once the decision to acidize has been made, the type of treatment, acid, and chemical additives for the job must be chosen. The treatment procedure must then be carefully evaluated. The complex chemistry of the acid reaction and its byproducts can be very damaging to the formation. Damage can be caused by precipitates, emulsions, changes in formation wetting agents, clay swelling or migration, and the reaction of the acid to downhole equipment, such as tubing, packers, and casing.
There are several types of acid used in oil field applications. By far the most common are the inorganic acids, hydrochloric and hydrofluoric. Organic acids, such as acetic and formic, are used occasionally.
The most commonly used acid is hydrochloric. Its popularity is due to its ability to dissolve large volumes of carbonate without forming damaging precipitates. The reaction of 1,000 gallons of 15% hydrochloric acid, HCl, will dissolve 1,840 pounds of limestone to form 331 pounds of water, 810 pounds of carbon dioxide, and 2,044 pounds of calcium chloride. The reaction of other HCl concentrations will differ as shown. At bottom hole pressures, the carbon dioxide and calcium chloride byproducts are usually in solution. As the spent acid returns to the surface, the carbon dioxide may break out of solution and become a gas. This carbon dioxide can serve as an aid in the post-treatment cleanup. The reaction of HCl with the other common carbonate reservoir, dolomite, magnesium carbonate, is similar to limestone except that the reaction rate is slightly slower, perhaps 1.5 times, at temperatures under 200 degrees Fahrenheit, or 93 degrees centigrade. 1,000 gallons of 15% HCl will dissolve 1,698 pounds of dolomite to form 332 pounds of water, 810 pounds of carbon dioxide, 1,022 pounds of calcium chloride, and 878 pounds of magnesium chloride.
Hydrochloric acid is available in concentrations as high as 35% by weight. Concentrations above 28% are not used in practice. In fact, concentrations above 15% were not used until recently, when inhibitors could successfully protect the equipment and tubulars against excessive corrosion. Common HCl concentrations used today are 7.5%, 15%, and 28%, with other concentrations available upon request prior to mixing.
Hydrochloric acid produces very few harmful byproducts when reacting with matrix minerals in most carbonate formations. The notable exception occurs when HCl contacts iron, usually in the form of the tubulars. Iron is dissolved in the acid and then carried into the formation. There, the iron-bearing acid reacts with the carbonate material. pH increases, and ferric iron, which can plug the formation, is precipitated. Additives such as sequestering agents can control this problem. A problem that cannot be controlled occurs in sour gas areas, where iron sulfide can react with HCl to form a very corrosive product that can damage the tubulars. This and other problems reinforce the need for acid formation solubility testing before the job. Hydrofluoric acid has its own set of problems. From a safety standpoint, it reacts with leather and natural rubber, and therefore must be handled with extreme care. It is also the only common acid that will react with clay minerals, quartz, glass, feldspars, and carbonates. Tests have shown that HF concentrations above 4% tend to deteriorate cores to such an extent that they become unconsolidated and then plugged, resulting in a decrease in permeability. In addition, the reaction of HF acid with the formation often forms a large volume of precipitates.
In fact, one major concern is formation damage resulting from precipitants formed by the reaction of hydrofluoric acid with carbonate material. This produces calcium fluoride, an insoluble byproduct that cannot be removed with any type of acid. This problem can be greatly reduced by the use of a hydrochloric acid preflush before the hydrofluoric acid treatment. It is for this reason that hydrofluoric acid is usually used in a mixture with hydrochloric acid. This mixture is commonly called mud acid. The optimum concentration of HCl and HF mixtures varies and should be based on acid solubility tests of the formation. In any case, hydrofluoric acid should never be used in any formation with a carbonate percentage above 20%.
Acid use guidelines presented by MacLeod, Ledlow, and Till in 1983 are based on the successful use of various acid concentrations. The most common solution of HCl and HF acids in high permeability reservoirs is 12% HCl and 3% HF. This table gives suggested acid concentrations for sandstones with various quantities of quartz, clay, feldspar, and chlorite. The recommended pre-flush fluid is extremely important and will prevent or reduce formation damage caused by harmful precipitates. In reservoirs with low permeability, 10 millidarcies or less, HCl concentrations need not exceed 6%. And HF concentrations 1.5%. Tests have shown that very low permeability sandstones, about 0.5 millidarcies, with a high clay content may require an HF concentration of only 0.5% to avoid damaging the formation. Phlorboric acid is another inorganic acid. It can remove clay damage and sustain production increases in cases where mud acid has failed. For example, as shown with a scanning electron microscope, the effect of phlorboric acid on sandstone is to dissolve the kaolinite material while leaving the quartz material relatively unaffected. In addition, phlorboric acid stabilizes clay material and prevents fines destabilization and subsequent pore clogging. Phlorboric acid procedures and effects are documented in the technical literature.
The inorganic acids, like hydrochloric, hydrofluoric, and phlorboric, are considered strong acids because of their ability to dissolve a relatively large volume of solids with a small volume of liquid. On the other hand, organic acids, any acid containing carbon, are generally considered weak acids. Their main advantage is that they are less corrosive to metals than HCl or HF acid. Therefore, organic acids are particularly useful in the treatment of carbonate formations where temperatures are extremely high or where contact time will be relatively long. Note, however, the inability of the commonly used organic acids to dissolve silica or clay material. Two organic acids that are used in the oil field are acetic and formic acids. Acetic acid is used during perforating because of the often lengthy periods when the acid remains in contact with the casing. Acetic acid can be used effectively in carbonate reservoirs. However, on a cost basis of carbonate dissolved per dollar of acid, HCl or formic acid is more economical.
Acetic acid is most commonly used in limestone reservoirs and produces calcium acetate, water, and carbon dioxide. Thus, 1,000 gallons of 15% acetic acid will dissolve 1,080 pounds of limestone. The resultant calcium acetate is a calcium salt and is of little concern since it is generally soluble in the spent acid. Because of its low corrosivity, acetic acid is also well suited to situations where aluminum or chrome-plated parts will contact the acid. Formic acid is stronger than acetic acid, but weaker than HCl. The reaction of formic acid with limestone yields calcium formate, also a calcium salt and thus soluble in the spent acid, water, and carbon dioxide. From this, we can calculate that 1,000 gallons of 15% formic acid will dissolve 1,420 pounds of limestone.
Frequently, formic acid is added to HCl to produce a mixture that is less corrosive and slower reacting than HCl. This combination works well as a retarded acid, allowing greater penetration in wells with temperatures up to 400 degrees Fahrenheit. However, in wells above 400 degrees, formic acid is used alone because the need for expensive inhibitors for the HCl makes its use cost prohibitive.
Other acids have limited oil field application due to their dissolving properties. If conditions indicate that one of the more commonly used acids could be harmful, then these less commonly used acids should be considered. Some of these are the inorganic phosphoric and sulfuric, and the organic citric, lactic, gluconic, and chlorocetic. Though not in general use, some are used in acid sticks or as sequestering agents in iron control. Specialty acids are designed to accommodate specific formation or treatment conditions. There are many types of specialty acids, and new acids are being tested for use in the industry. Engineers must stay abreast of this technology and discuss acids and their applications with the service companies. Your manual discusses several specialty acids, including retarded acids and foamed acids. The selection of acid and additives depends on formation composition. Lab tests are valuable in such determinations. Thin section studies of reservoir rock are effective in identifying clay material and rock composition. The scanning electron microscope is capable of revealing much greater detail. It can be used to find minerals that can potentially damage the reservoir flow channels. Once found, precautions can be considered and remedies incorporated in the treatment design. Additives to the acidizing fluids are often necessary to prevent damage to the formation and tubulars. The amount of chemical additive depends not only on the formation, but on the acid and the type of treatment. Corrosion inhibitors are one type of additive that is used in all acid treatments. The reaction of 15% HCl on 2 test coupons, representing J55 tubing, illustrates the significance. 12 hours of exposure to the inhibited acid causes no damage to one sample, while the coupon submerged in uninhibited acid shows considerable damage. Surfactants, another common additive, are used to prevent acid-oil emulsions, prevent sludge buildup, and change formation wettability. For example, the mixing of acid and crude oil often forms a thick, viscous emulsion that cannot flow through the reservoir. This impairs treatment fluid recovery. Emulsion testing before the acid treatment can help to identify the type of surfactant necessary to prevent the formation of stable emulsions. Though emulsions can still form, the surfactant will rapidly break them, and fluids can then be easily recovered. Surfactants can sometimes minimize sludge problems. Sludge is a solid that forms when acid contacts asphaltic crude oil. Sludge is extremely difficult to dissolve and will adhere to reservoir rock, causing a decrease in permeability. Surfactants can also alter reservoir wettability. Here, 2 beakers contain identical samples of water and oil with a red dye. The beaker on the left also contains cationic surfactant. Water-wet sand grains are poured into both beakers. Red-colored sand indicates grains that have become oil-wet and illustrates the change in wettability that occurs from treating anionic sandstone with cationic surfactant. In the reservoir, this increases the residual oil saturation near the wellbore and reduces the permeability to oil. Other common additives include sequestering agents, clay stabilizers, bacteria control agents, friction reducers, fluid loss additives, and fluid recovery agents such as nitrogen or carbon dioxide.
There are no universal additives for solving formation acidizing problems. Therefore, both field results and lab tests should be utilized for optimum results. The engineer must decide on the most cost-effective treatment design after considering all the available data and treatment options. Since your manual covers this material in much greater detail, This is a good place to pause the tape, read Unit 1, and work the exercises. In this unit, we'll show how to design and monitor an acid treatment. We'll look at two case histories of acidizing carbonate formations in this sandstone matrix acid treatment. We'll select acid types and consider the appropriate additives. Our discussion of treatment design will include a method for calculating injection rates, treating pressures, and fluid volumes. We'll also observe the procedures involved in conducting an acid treatment. And we'll review the required surface treating equipment and prudent quality control measures. Let's begin with the first case history.
Well, this first example we're going to look at is a workover which involved a matrix carbonate acid treatment to restore production. This particular well in West Texas was a carbonate at about 6,000 feet, and a casing leak developed which cut production from about 4,000 to 2,000 barrels per day. The workover that was required to repair the casing leak substantially damaged the formation. We designed a small matrix acidizing treatment using 15% hydrochloric acid at a concentration of 150 gallons per foot, which was treated at below fracturing pressure.
In this matrix acid treatment, did you recommend pickling the tubing before the job?
Pickling is very important, particularly when there are iron compounds in the reservoir, or if you're using a work string which may have been rusty, or something where iron might be put in solution during the acid treatment. In this particular case, we used a workover string that had been treating acid, that had been used in acid treatments in other wells, so we felt pickling was not important.
What type of additives did you recommend?
After selecting the acid solution as 15% hydrochloric acid, we performed emulsion tests in the laboratories with various cationic non-emulsifiers. A specific non-emulsifier was selected at a concentration of 2 gallons per thousand, which indicated in the laboratory that there would be no problem with emulsion formation or problem with sludge following the acid treatment.
How long was the well shut in following the treatment?
Following the treatment, the acid load was recovered as soon as possible, or in this case, almost immediately. As in most sandstone and carbonate acidizing techniques, it's generally best to recover the treatment as soon as possible. This removes the fines from the formation and also allows acid that hasn't spent to dissolve formation contaminants and formation rock itself on the way out into the wellbore. The most important consideration in this treatment was to recover the treatment load as soon as the treatment was finished and to ensure that there would be no subsequent emulsion problems, which was done by the use of surfactants and laboratory testing prior to the acidizing treatment.
How successful was the treatment?
After the acidizing treatment, you will note that we restored the production of the well to what it was when the well was initially completed.
Tell us about the second case history now.
Okay, this next case history is in a North Sea well. This particular well produces from a chalky limestone reservoir in a deep horizon in the North Sea. The most important design consideration in this case was the vertical extent of the reservoir, approximately 400 to 500 feet. The intent of our design in this particular well was to maximize flow capacity and remove wellbore damage.
What did you consider in selecting the acid type?
And we selected a multi-stage treatment using 28% hydrochloric acid. 28% hydrochloric gives us greater limestone dissolving capability and also some retardation.
What do you feel is one of the most important factors in designing a fracture acidizing treatment?
To get the maximum productivity increase from fracture acidize, we need to get acid penetration. As the live acid penetrates down the created fracture, it will leak off into the fracture face. Therefore, to maximize penetration, fluid loss control is an absolute must.
What did you consider in determining the treating technique?
The intervals of these wells were approximately 400 to 500 feet. We were limited due to rate, so many stages or multi-stage treatments were the prime consideration. Several of the wells were done in at least 20 stage treatments. Of these stages, there are 3 sequences that are run. The first sequence is a viscous pre-flush. This contains fluid loss additive, which is able to extend the acid penetration. The viscous pre-flush is a non-acid stage, which is pumped ahead of the acid. The acid then follows, and because of its mobility difference, fingers through the viscous pre-flush and can extend acid penetration. Following the acid, then there is a diverting stage, which contained benzoic acid flakes, which allowed the subsequent stages to be diverted to less permeable areas.
Did you feel there was a need to catch post-treatment production samples?
On some of the initial treatments, samples were taken to be sure that we did dissolve, or we did spend all the acid on the formation rock. The samples were taken to just primarily test for iron content and for the concentration of the acid. Some of the initial treatments we did not overflush the acid substantially enough, so we had live acid returning, which of course did nothing to improve productivity of the well. So we increased the overflush on the stages after we gained some experience in this particular field with the acid volumes and the overflushes.
How successful was this treatment?
After these relatively large fracture acidizing treatments, we came up with a negative skin of -5 and -6, which is about the theoretical optimum that you could expect from these type of treatments. Relative to productivity ratios ranged in the neighborhood of 4 times to 8 times the initial production prior to the acidizing treatment.
Now that we've looked at 2 treatments of carbonate reservoirs, let's consider a matrix acid treatment of this sandstone reservoir.
We'll review the design carefully and then observe its execution firsthand, including procedures, equipment, and quality control.
This well was completed in a 30-foot sandstone section. Porosity is approximately 15%, relative permeability to oil is approximately 90 millidarcies, and relative permeability to water is 30 millidarcies. The formation composition analysis has shown that the sandstone formation has less than 10% HCl soluble components, so an HCl-HF acid seems appropriate. The pressure transient analysis of the buildup data from the subject well shows that a skin factor of 8.0 is severely limiting production. The skin damage is believed to be caused by the kill fluid used when artificial lift was installed. Because the damage is probably shallow, acid penetration of several inches should be enough to restore well productivity. Based on reservoir permeability, composition, and results of previous acid treatments on nearby wells, a 12% HCl, 3% HF acid has been chosen. A pre-flush with 15% HCl and an after-flush with 3% ammonium chloride will also be used.
Because this reservoir is partially depleted, the fracture gradient has changed from the initial fracture gradient of 0.6 psi per foot. The current fracture gradient, and then the maximum treating pressure, can be determined in several ways. For our example, we have chosen a method that requires determining Poisson's ratio first. Based on values for the fracture gradient, overburden, reservoir pressure, and depth, it is calculated to be 0.226. Using this constant, the current reservoir pressure of 3,000 psi, and a well depth of 9,200 feet, we calculate the current fracture gradient to be 0.523 psi per foot. At this point, we can also determine that the bottom hole treating pressure should not exceed 4,812 psi. A safety factor of 300 psi will be used to mitigate the uncertainty of this calculation. Next, we create a table which indicates the gradient, in psi per foot, and hydrostatic pressure of the fluids that will be used during the treatment. The necessary fluids include brine with a gradient of 0.50 psi per foot and a hydrostatic head of 4600 psi. The properties of the pre-flush, HF acid, after flush, and diesel oil displacement fluid are tabulated. Finally, to determine the maximum treating pressure, we consider the depth of the well and the total hydrostatic head of the fluids in the tubing. In our example, this involves looking at the 9,200-foot 2 3/8 inch OD tubing and its 1,500-gallon volume. The maximum surface treating pressure is equal to the bottom hole fracture pressure minus the hydrostatic pressure minus the safety factor. Completing this calculation yields a maximum surface treating pressure of 197 psi. This treating pressure could increase to 445 psi when the 15% HCl fills the tubing, to 482 psi when the ammonium chloride afterflush fills the tubing, and to 1,264 psi when the diesel displacement fluid fills the tubing. The injection rate at which the HCl pre-flush and HF acid will be pumped into the formation depends on the type and extent of formation damage. We can estimate the injection rate for a damaged well based on the skin factor calculated from the pressure transient analysis. To do this, we must first calculate the injection rate for the undamaged zone. Using Darcy's radial flow equation, this injection rate in barrels per minute is 4.917 times 10 to the minus 6, a constant, times the permeability in millidarcies, times the formation height in feet, times the pressure differential between injection pressure and reservoir pressure, divided by the formation volume factor, times the acid viscosity, times the natural log of the drainage radius divided by the wellbore radius, or 0.587 barrels per minute. This injection rate will be greater as soon as we consider the radius of injection instead of the drainage radius. But to do that, we must first calculate the total treatment volume, which includes pre-flush, acid, after-flush, and displacement fluid. The HCl pre-flush required in HF treatments serves two purposes: to displace the formation fluids so that no potassium, sodium, and calcium ions will mix with the HF acid, and, more important, to prevent the precipitation of calcium fluoride, an insoluble solid, by dissolving any calcium and magnesium carbonate. To accomplish this, most matrix treatments are designed so that the radial depth of the pre-flush will be 3 to 5 feet. We can calculate how much HCl pre-flush is required by using a constant, the porosity, the formation thickness, the radial depth, and the wellbore diameter. The pre-flush volume in our example, then, is 1,833 gallons. Unless we are able to perform acid tests on core samples, the volume of HCl-HF acid is more complicated to determine. We generally assume that a matrix acid job using HF acid will penetrate only 3 to 6 inches before it is spent. Core flow tests have consistently shown that core permeability is reduced until 30 to 50 pore volumes of acid have been produced through the core. Many sandstone core tests have indicated that it is reasonable to use an acid volume of at least 30 times the pore volume. Thus, using a factor of 40 times the pore volume for our subject well, the recommended volume of acid is calculated to be 4,110 gallons. We calculate the volume of the afterflush the same way we calculated the volume of the pre-flush. It is also 1,833 gallons. Now, rounding off the fluid volumes, The pre-flush is 1,850 gallons of 15% HCl. The acid is 4,200 gallons of 12% HCl, 3% HF, and the after-flush is 1,850 gallons of ammonium chloride. The volume of diesel required to displace the ammonium chloride to the perforations is 1,500 gallons. The total treatment volume, which must be pumped at pressures below formation fracture pressure, is 9,400 gallons. These volumes support the following common rules of thumb used in sandstone acidizing. Pre-flush and after-flush volumes of 50 to 75 gallons per foot, and acid treatment of 100 to 150 gallons per foot. If no acid solubility tests are available, these rules of thumb can be applied. Of the 9,400 gallons of total treatment, only 7,900 gallons will penetrate the formation, since 1,500 gallons will remain in the tubing. Thus, we can now calculate the radius of injection as the volume of fluid that penetrates the formation, 7,900 gallons, divided by the quantity 7.48 gallons per cubic foot, times pi, times porosity, times formation thickness, all to the 1/2 power, or 8.6 feet. Using this value in Darcy's radial flow equation, we calculate the anticipated injection rate for the undamaged reservoir to be 1.37 barrels per minute. To complete the calculation of the anticipated injection rate into the damaged reservoir, the productivity ratio must first be calculated and then applied to this undamaged injection rate. The productivity ratio is calculated using the drainage radius, the wellbore radius, and the skin factor. This yields an injectivity decrease factor of 0.487. The injection rate into the damaged well is therefore equal to 0.487 times 1.37 barrels per minute, or 0.67 barrels per minute. Note that this is an initial rate only, and that it will increase as the damage is removed. It should also be emphasized that if the injection rate is calculated to be below 1/4 barrel per minute, then the treatment must initially be pumped intermittently as follows. Acid is pumped until the maximum treating pressure is reached. The pumps are shut down until the pressure bleeds off, and the process is repeated. Time constraints must be considered in the design of an acid treatment. The calculated injection rate of 0.67 barrels per minute would require 334 minutes, or 5 hours and 34 minutes, to pump the total treatment. The spent acid should not be left in the formation for extended periods of time because precipitates, emulsions, and sludge can form and have harmful effects.
Based on the calculated injection rate of 0.67 barrels per minute, 2 hours and 30 minutes will be required to pump the HF acid. If the treatment injection rate is greater than expected, a minimum contact time of 2 hours will be needed to realize significant acid reaction and prevent the recovery of very strong acid. On the other hand, if the acid injection rate is too low, that is, less than 1/4 barrel per minute during the hydrofluoric acid stage, it may be necessary to reduce the acid volume and retreat the well at a later date. Okay, let's look at the equipment and some quality control measures.
Any water that will be used as a pad or flush fluid should be tested for chemical composition and compatibility with the acid and formation fluid. Fluid and equipment cleanliness is extremely important in matrix acidizing. The tanks should be cleaned before filling them with either acid or water. Small amounts of debris can cause considerable damage during an acid job. Next, the condition of the tubing or work string should be checked. Whenever possible, the engineer should inspect the tubing or work string before it is run. Residual rust, scale, paraffin, sludge, and other debris inside the tubulars can be pumped into the formation and decrease well productivity. If the tubing is dirty, it should be cleaned before being run into the hole. If the engineer suspects that dirty tubing is in the hole, then acid or another equally effective cleaning agent should be circulated. The major components required for this matrix acid treatment are an acid transport, a pump truck, and a high-pressure filter unit. The acid transport has 3 independent storage compartments. Contents and volumes are clearly identified. The most important feature of this transport is the diesel-powered pumps used to remix acid and additives that may have segregated in the acid tanks due to density differences. The pumps force air to the bottom of each compartment to effectively mix the contents. This internal circulation is imperative to ensure complete mixing of fluids and should be done just before the acid is injected. Many service companies do not do this on a routine basis, so the engineer must specify this procedure in the original job proposal. Low-pressure lines transfer the treating fluid from the transport to the pump truck. This pump truck is used only for acidizing and gravel packing operations, never for cementing. Such exclusive use eliminates concerns about contamination from other fluids and cement. 2 open 10-barrel tanks located at the front of the pump truck are used to measure the load water. The 25-barrel mixing tank at the rear of the truck is provided for situations where the mixing of gelled fluids is required. It will not be used on this job. Triplex pumps are also mounted on the rear of the pump truck. Powered by a diesel engine rated at approximately 300 horsepower, these pumps are capable of displacing from 8 barrels per minute at 0 psi to 1/2 barrel per minute at 10,000 psi. The triplex pumps draw acid out of the low-pressure line from the transport and discharge acid into a high-pressure line that leads to the high-pressure filter unit. The filter system is extremely important, especially in sandstone matrix acid treatments. Here, several 2-micron filters remove solids from the treating fluid. These solids could severely damage the formation. Further, if the unit's intake and outtake pressure differential were to exceed 45 psi, there would be a danger of collapsing the cartridge filters and contaminating the reservoir. Therefore, pressure differential is displayed on a gauge and monitored throughout the job. Finally, acid exits the filter system through high-pressure lines connected to the wellhead. The engineer should review the service company's call sheet to ensure that all the necessary additives are available on location in the correct quantities. Certain additives must be mixed on location. Others can be mixed at any time. After the acid tanks have been thoroughly mixed, the engineer must be sure that the concentration of the HCl acid is checked in order to confirm that it falls within design parameters. This is done, preferably, with a titration kit, but it can also be performed with a hydrometer. To determine acid strength by titration, the following equipment and reagents are needed: 2 5 to 10 milliliter syringes, a 1 milliliter pipette, a beaker, distilled water, approximately 50 milliliters per test, 2 normality sodium hydroxide solution, and phenolphthalein indicator solution. Here, the chemist starts the procedure by placing 10 milliliters of the acid sample in the beaker. Next, distilled water is added, followed by 2 drops of phenolphthalein indicator solution. While stirring the acid sample, the chemist uses the other 10 milliliter syringe to add the 2N sodium hydroxide solution by drops until the acid turns a distinct pink. The chemist then records the amount of sodium hydroxide solution used and determines the HCl strength from a table or chart based on this recorded volume. In this case, 43.6 milliliters of sodium hydroxide corresponds to a 15% HCl strength.
Thanks. This method gives the acid percentage within plus or minus 1%. This same procedure can be used to determine the total acid strength of an HCl-HF mixture.
In the other method for determining acid strength, the hydrometer should have a range of specific gravities from 1.0 to 1.2, or a Baum range from 1.0 to 25.0. Once the hydrometer reading is obtained, the acid strength can be determined from a table or chart. After confirming the acid strength and additives, the engineer should review the well-bore diagram with the service company personnel. Everyone, including service rig personnel, should be made aware of the maximum surface treating pressure and the pumping time. A pin recorder documents treating pressure and time throughout the job. Once the job has begun, injection rate and pump pressure are displayed at the operator's control station on the pump truck. Injection rate can be read directly off the gauge or calculated from pump plunger size and strokes per minute. The acid tanks are gauged throughout the job as a safety precaution to confirm the accuracy of the pump rate.
All treatments should be closely monitored throughout the job. Let's look at some considerations.
This treatment has the advantage of a computer monitoring system. It records basic well data, downhole equipment and conditions, and treating fluid volumes and properties. Treatment pressures and injection rates are recorded on a time-coded scale. Notations can be included on the chart to indicate significant events such as pre-treatment test details, slurry stage, anomalous pressure behavior, and perf ball response. The computer also prints a summary of the job once the treatment is over. This computer system, which is also used for gravel packing operations, provides an excellent permanent record of the acid treatment. Such printed data is useful in re-examining wellbore hydraulics and reservoir responses that occurred during the treatment. As a result, subtleties can be detected that can lead to improved treatment designs. Additional information on wellbore hydraulics, including friction losses through the perforations and tubulars, is presented in PE 305, Fracturing. Preparation for flowback or swabbing is made prior to pumping the acid. The shut-in time should be kept to a minimum after most treatments to reduce the risk of harmful precipitants. Usually 15 to 30 minutes of shut-in is required to allow for the safe rig down of the service equipment and rig up of the flowback equipment. In this case, it was decided that the well would produce directly into the production facility. It is important to catch samples of the produced treating fluid after the job. Samples should be obtained periodically until approximately 500% of the treating volume is recovered. The fluid should be tested for types of solids, including amounts and sizes, the strength of the acid, iron content, emulsions, precipitates, bacteria, and approximate oil-water cut. The flowback after the treatment should be restricted, especially for sandstone wells. Excessive drawdown can result in the plugging of the formation by fines and precipitates. Sandstone reservoirs generally respond well to acid treatment. Sometimes, however, treatments yield poor results. Unless the reasons for failure are known, future treatments are also likely to fail. Williams, Gidley, and Schechter, in the SPE monograph of Acidizing Fundamentals, list 8 common reasons for the failure of matrix acid treatments. The same matrix acidizing methods used in sandstone reservoirs can be employed in carbonate reservoirs. The very high solubility of carbonates, however, results in an undesirable phenomenon called wormholing. Initially, the acid forms several large pores in the carbonate material. These pores readily accept acid, lengthening in an unpredictable manner until the acid is spent. The erratic nature of this phenomenon makes predicting acid etching patterns very difficult. Limiting the wormholes results in a more effective matrix acid treatment. Laboratory tests have shown that wormhole length is limited by fluid loss and not by acid reaction rate. Either a viscous emulsified acid or acid with a fluid loss material is effective.
The results of acid treatments can vary tremendously depending on the characteristics of the reservoir. Wellbore washouts and matrix treatments will not increase production unless the wellbore or near wellbore has an accumulation of scale, paraffin, clay material, or other debris that needs to be removed. Acid fracture treatments will not be successful on a low permeability reservoir unless the reservoir can retain a highly permeable induced fracture, or in a higher permeability well unless there is deep reservoir damage to be removed. Your manual contains the material covered here, so please read Unit 2 and work the exercises. Good luck.